Hi everyone. As Alovani introduced me, I'm a PhD student in quantum research group of Stellenbosch University. And actually, I was supposed to talk about my experience in hackathon, but Donovan will do that after me. And I changed the topic yesterday. And it's a potential application of quantum computing plus HPC, a very, very short introduction. Because it was like a very, very short notice for me. It was just like yesterday that I realized that I need to give a talk here. When I looked at the program, the table of content of your program, I didn't see anything about quantum. It was standard Bash, Python, machine learning, statistic, and this kind of stuff. So let's make it a little quantumish, at least for like 20 minutes. So I hope that next year maybe we can have a specific part for quantum computing because it's another trend along with HPC, along with the machine learning, deep learning, neural network, and this kind of stuff. And I'm going to just talk about like a 7-8 minutes, and then after that, Donovan will share his experience about hackathon and why it's important to participate and attend to this kind of events. Okay, just one slide about the quantum technology. The quantum technology usually is categorized to 4 or 5 different category. One of them is quantum computing that I'm going to just cover with a couple of slides. Another category is quantum communication and networking, which is related to quantum internet. And another one is quantum simulations. In some specific literature, people consider quantum simulation as a part of quantum computing. And quantum sensing, metrology, and imaging, and to this part of the technology of quantum, this part of the quantum technology is concerning with making better sensors, like what we have in detecting gravitational wave, this kind of stuff. But I'm just going to cover this quantum computing part. This is I think, a nice picture about the investment in the quantum technology in different countries. We are here, South Africa. It's like $3 million or 54 million rand, and then you can calculate the conversion factor between dollar and rand. But in comparison to countries like a US and like Canada, China, and I don't know, European quantum flagship, they are it's nothing actually, but it's better than if you can see in many countries, still we don't have either we don't have statistics for the investment, or they don't start, they haven't started the investment in quantum technology in general. But the order of magnitude in Canada, US, I don't know, UK is like $1 billion, but here we have in 3 million. Okay. And this is quantum technology. It's not just quantum computing. Okay, what is quantum computing? Is just one slide. First of all, it is it is fundamentally different from the classical computing. It's not just a next generation of classical computer or faster classical computer. It is fundamentally different. Fundamentally, I mean that we have 0 or 1 bits in classical computer, but here we have qubits. How can we realize these qubits? It's another story. We have different hardware, different platform, different physical realization for this qubit, like spin, like the photon, like superconducting qubit, ion trap, this kind of hardware. But at the end of the day, when you measure it, it is like strings of bits. We have two important feature or characteristics of quantum computing, which is called superposition and entanglement. So if you have a qubit or quantum bit, you can have a superposition of two states. It's a little weird, I know, and it is what it is. And we can use this feature, this characteristic, to store more information in just a couple of qubits, like let's say 50, 100, and we can potentially solve some problem with this kind of qubits, and it is intractable in classical computing. And when I'm talking about entanglement, I mean that these 2 or 3 or more qubits can talk to each other. And this is also very important in quantum computing. Another properties of the quantum mechanics in quantum computing is tunneling. I'm not going to talk about this one, but this is also very important, is non-classical properties. Okay, this is quantum computing. At the moment, there are two terms I just want to mention: NISQ, NISQ, and FTQC. Our goal is to reach to this point, fault-tolerant quantum computing. But at the moment, we are in this era. What do I mean that we are in this era? NISQ era represents the current stage of quantum computing where quantum device face limitation due to noise. This is very bad for our quantum computing hardware. And also we have errors. That's why we have a specific field which is called quantum error correction. And the number of qubits that we have, it's approximately 100 to 1000. But our goal is to reach to this point, and then probably we can have a disruptive practical advantage, and then they can completely change many industries. So in this point, I mean, we have 1 million, 10 million qubits, and we have error correction that we can correct those errors, and then we can compute that some specific problem that is intractable on quantum computer. And okay, so but for the near term, for the NISQ era, we expect that the most valuable near-term quantum application will be hybrid. What do I mean by hybrid? I mean, I will show you in the next slide, but it's a combination of classical computer, which we expect to perform it on the high performance computing HPC, and quantum part. I will show you in the next part. And these are a bunch of potential application: chemistry, material science, drug discovery, finance, logistic, machine learning, of course, aerospace, automotive. And sometimes in the literature, you will hear something like quantum supremacy, which is started in 2019 by Google. And then people started to think about it more realistically. So it changed it to the quantum advantage and utility, usefulness. And what is important for us is practical quantum advantage. Okay. Sometimes you can solve a specific problem that is intractable on a classical computer, but it doesn't have any advantage. You could just solve the problem. But what is important for us, and what is important for investors to invest in your company or your startup, is practical. So what do I mean by the hybrid quantum classical computing? I mean that it's the combination of the strengths of the both quantum and classical paradigm. We have something which is called parameterized or variational quantum circuit, the PQC or VQC. It is somehow, in some sense analogous to classical neural network. So you have a parameter, your circuit have a parameter. This is the quantum circuit, and you have a parameter in your quantum circuit, and some part of the calculation is still very hard for quantum computing, but it's a kind of easy task if we perform it on a classical computer. So some part of the problem, we are running the quantum circuit on a quantum processor, measuring, for example, the n. Okay, this is a VQC. I forgot to mention that. This is a variational quantum circuit. This is a general term, but this one in the red box is a specific example. So variational quantum eigensolver is a specific example of variational quantum circuit, which is a hybrid algorithm. So here, for example, VQE, our goal is to find the ground state energy of a quantum, of like a system. Could be a solid state physics, it could be a chemistry problem. But the important part is in this kind of problem, running a quantum circuit on a quantum processor, we're measuring the energy, you can see here. And then using classical optimizer, this is just a cluster of supercomputer. And the optimization algorithm to adjust the parameters of the quantum circuit to minimize the energy. So the optimization part, we can do this part in the, and there are lots of papers out there that did this procedure. So in the like a near term, we expect to have some advantage from this kind of algorithm. And how much time do I have? Okay. There are different categories of like an archetype. Like we have factorization, we have simulation, optimization, machine learning, sampling, and there are the industry that can use this kind of algorithm. Okay, for example, we know that this is the chemical probably use the quantum simulation, and for example, the I don't know, this is TTL is travel, transport, logistic. It's a, for example, if you have an optimization problem with lots of configuration, with lots of combinate, it's like a combinatorial problem, probably you need to use optimization, and so on and so forth. And then I will share this slide. Maybe you can look at it after my talk. This is also similar to the previous slide, but at the this is a report from McKinsey journal, and they also mentioned in the near term leveraging a hybrid operating system to distribute a complex problem between HPC that we have in CHPC center and quantum computing can bring a bigger computational advantage. And except cryptography, which we need, I think, fault tolerant, but we can work in these three areas, simulating problems like quantum chemistry, I don't know, solid state, molecular dynamic, optimization, logistic problem, and of course, machine learning problems. Okay, there are different companies that working in this hybrid platform. I just want to give you a quick example and then finish my talk. And then if you have any question, you can send me a message on different social media platforms. Okay, one of them is NVIDIA. You know that. We have, I guess, NVIDIA V100 something in the CHPC center. But NVIDIA also are involved in quantum industry. They don't make like QPU, and QPU, I mean quantum processing unit. They don't make any hardware, but they have a platform which is called CUDA Quantum that delivers a unified programming model for quantum processor. Actual or emulator, what do I mean? I will show you what do I mean. Actual is there are some companies, big companies like Google, IBM, Quantinuum, and different companies that Rigetti, then making this quantum processing unit, this hardware, And then with this platform, you can have access to these kind of resources. But the interesting thing is that you can, if you want to run the hybrid algorithm here in this platform, you have access to the CPUs, GPUs, QPUs, and probably they are optimized for that specific task. I'm not very expert, but maybe in the near future, our policymaker also can think about to reach out to NVIDIA CUDA Quantum as well. Okay. And there are some benefits. I told you it's a hybrid. They tested the VQE algorithm, the 287 speed up, and it's an open platform, and it's very important that it is easily integrated with GPU accelerated and so on and so forth. Okay, there is also another thing which is called Q-Quantum. What is the difference between this one and the previous slide? This one is just a simulator that used like a highly performant multi-GPU, multi-node of NVIDIA. So, and then you can connect this with these two famous in our world at least, Qiskit and Google Circ packages in Python to simulate your quantum system. And it is very simple in terms of coding. For example, here, they show that if you want to solve a variational quantum eigensolver to find the ground state energy of a system, you just need to change this part. For example, if you want to use the simulator that I show you here, like a multi-GPU, multi-node, this is just a simulator. You can use this part, Q-Quantum. But if you want to use the actual quantum computer, actual QPU, you can write a specific name here. For example, this is the Quantinium, and this is a big company in making hardware and software in quantum computing industry. And then you can change it, and then and you can see this is because this is the simulator. Your simulation is better than this one. I don't want to go to the detail of what is the simulation, what is our Hamiltonian, and so on and so forth. And okay, let me just, I have, I think, one more slide, and then I will finish. If you are interested, there are also other companies that are working on this hybrid platform, like Microsoft. There is a nice, like 30 minutes Microsoft Quantum Innovator webinar series that they talk about how a hybrid of classical and quantum computing in a cloud enable a new class of application, and how they can combine this AI, ML, and to quantum computing with HPC automation. And there is a nice blog post here, then you can read. And I guess, yeah, thank you very much. And I should mention this question, probably this will be one of the questions. Let me just answer it now. The progress in quantum computing is being made, but if you are thinking about the practical advantage, the practical applications of the technology are still likely years away. And we hope that there are some potential application. That's why many people are doing their PhD in quantum computing as well. Okay, thank you very much. I think I was supposed to talk like 7-8 minutes, but it's a little more. And thank you.
Thank you. Thank you, Omid, for a nice presentation. So we're running late.